Welcome to the third lesson of the PLC programming course, developed and reviewed by Professor Roberto Araujo Lima. In this lesson, we will be exploring the basics of Boolean logic and its importance in understanding PLC programming languages. Boolean logic is the foundation of PLC programming and is essential for creating effective and reliable control systems. By the end of this lesson, you will have a solid understanding of the basic Boolean logic functions and how they can be used in PLC programming. So let's get started. George Boole was born on November 2, 1815, in Lincoln, England. He was self-taught in mathematics and was heavily influenced by the works of mathematician and philosopher Augustus de Morgan. Boole attended Lincoln College, Oxford, where he studied mathematics. He later became a professor of mathematics at Queen's College, Cork, in Ireland. Boole's contribution to technology through Boolean algebra was his development of a mathematical system for representing and manipulating logical statements. This system is now used in the design of digital circuits, including those found in PLCs. Boole's work laid the foundation for modern computer science and has had a profound impact on the development of digital technology. Sadly, Boole passed away at the relatively young age of 49, but his legacy continues to shape the world of technology today. In this lesson, we will be exploring the basic Boolean logic functions that are essential for creating sophisticated control systems. Specifically, we will be covering the following functions: identity function, AND function, OR function, NOT function, NAND function, NOR function, XOR function, XNOR function. Each of these functions performs a specific logical operation and plays a crucial role in PLC programming. So let's dive in and learn how to use these powerful tools to create effective control systems. The Boolean function identity, also known as the zero identity, is a simple but fundamental concept in Boolean algebra. It states that the sum of anything and zero is equal to the original value. In other words, when you add zero to any Boolean value, true or false, the result is always the same as the original value. For example, if A is true, then A0 will also be true, and if A is false, then A0 will also be false. This may seem like a trivial fact, but it's actually a fundamental property of Boolean algebra and plays a role in more complex logical operations and expressions. So in summary, the Boolean function identity states that adding 0 to a Boolean value doesn't change its value. And this simple but important property underpins many of the more complex logical operations used in PLC programming.
In this example, we have a representation of the identity function in a simple application with the PLC. Note that we have an open contact with a button connected to input I2 of the PLC. We also have a lamp connected to output Q1 of the PLC. Next to it we have an example of programming in ladder language. The concept of the identity function is being executed in this example. When the CLP enters operating mode, it performs a scanning process, where it reads the input signal, processes the program and updates its output. In this case, input I2 is equal to 0. After program processing, output Q1 is updated and its signal remains at 0. If someone presses button I2, its contact closes and the input logic level goes to 1. After program processing, output Q1 goes to 1 and the lamp lights up.
The AND function is a logical operation that returns true if all of its inputs are true. It's represented by the symbol AND in many programming languages. The AND function is often used to require multiple conditions to be met before a certain action is taken. For example, in a PLC program for a manufacturing machine, the AND function could be used to ensure that a safety switch is closed and a part is in place before starting the machine. Here's an example of how the AND function might be used in a PLC program. If safety switch true and part in place true, then start machine. In this example, the start machine function will only be called if both the safety switch and part in place variables are true. In summary, the AND function is a powerful tool in PLC programming that allows developers to create control systems that respond appropriately to complex input conditions.
Example of an electrical circuiting series, performing the function E. The open switches represent logic level 0, the closed switches represent logic level 1, the lamp is the response of this circuit. The lamp will only light up when both buttons are pressed, closing the circuit. Observe the truth table of the function and it performs a Boolean multiplication of the input variables, in this case the a and b keys. There are 4 possibilities, where only in the last condition where we have 1 multiplied by 1, the output will be 1, in the others the output will be 0. Respecting the series electrical circuit from the previous example. In this example we have a representation of the function and, in a simple application with the PLC. Note that we have an open contact, with a button, connected to input I2 of the PLC, and another open contact with a button to input I3. We also have a lamp connected to output Q1 of the PLC. Next to it we have an example of programming in ladder language. The concept of the AND function is being executed in this example. When the CLP enters operating mode, it performs a scanning process, where it reads the input signal, processes the program and updates its output. In this case, after program processing, output Q1 will be equal to 1, when inputs I2 and I3 are true. The OR function returns true when at least one of its inputs is true. For example, the expression A or B is true if A is true or if B is true, or if both are true. When associating the electrical circuit, we have the switches connected in parallel, representing the OR function. The lamp will be off when the switches are open, that is, at logic level 0. Any other combination, the lamp will light up. In the truth table we have the Boolean sum being performed through the OR function, where we can observe the 4 possible situations: 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 is equal to 1. In this example we have a representation of the OR function. In a simple application with the PLC, note that we have the same connection of the 2 buttons at input I2 and I3 of the PLC, in addition to the lamp at output Q1, similar to the example of the AND function. Note that to execute the logic of the OR function, a program made in ladder language was developed with 2 open contacts with addresses I2 and I3 in parallel, similar to the electrical circuit. When the buttons are not being activated, the Q1 output is equal to 0, in any other combination the Q1 output is equal to 1. The NOT function inverts the logical value of its input. For example, the expression not A is true if A is false and is false if A is true. See the NOT logic gate and the truth table. Note that if input A equals 0, its output equals 1. If input A equals 1, its output equals 0. In this example using the PLC, notice that we have a normally open button connected to the PLC I2 input, and again we have a lamp connected to the PLC Q1 output. The behavior of the program represents the NOT function. Note that in the program developed in ladder language the closed contact works as a signal inverter. If input I2 is 0, that is, if the button is not pressed, output Q1 will be equal to 1. When the button is pressed, input I2 will be true and output Q1 will be off. The NAND logic function is an operation that returns false only when all its inputs are true. In other words, the NAND function is the negation of the AND function. Returns true in all other cases. The truth table of the NAND function is as follows. In the truth table, we can observe the behavior of the NAND function, basically a Boolean multiplication, inverting the result. In the example with the PLC, we have the configuration of the 2 switches and the lamp connected to the PLC, similar to the previous examples. Note that in ladder programming, we connect the input contacts in series, to perform Boolean multiplication, and through an auxiliary memory, we are inverting the result of the logic. The logical function NOR is an operation that returns true only when all its inputs are false. In other words, the NOR function is the negation of the OR function. It returns false in all other cases. The truth table of the NOR function is as follows. Observe the behavior of the NOR function. Basically we have a Boolean sum, inverting the result. See the example in the PLC below. Note that we have the PLC connection the same as the previous example, but now the ladder programming corresponds to the NOR function. We have two inputs in parallel, and the auxiliary memory, being responsible for inverting the result of the combination. The ZER function returns true when one and only one of its inputs is true. Otherwise, that is, if the two inputs are equal, both true or both false, the ZER function returns false. The truth table of the ZER function is as follows. Note that the output is true only when one of the inputs is true, that is, if there is a difference between the input variables. When the inputs are the same, the output is false. See below the application example with the PLC. In this example we again have the two keys and the lamp as output. Observe the behavior of the ZER function in PLC programming. The lamp will only light up when there is a difference in the input variables. Otherwise, the lamp remains off. The ZNOR logical function is the negation of the ZER function. It returns true when the two inputs are the same, both true or false, and false when the inputs are different. The truth table of the ZNOR function is as follows. Now we have true output only when both inputs are equal to 1 or equal to 0, otherwise the output is false. Finally we have the last example in the PLC, representing the ZNOR function. See that we have the connection of the switches in the lamp, the same as the previous examples. Now ladder programming represents the ZNOR function, keeping the lamp on only when the input signals are equal, otherwise the lamp will be off.
Thank you for attending today's lesson on Boolean logic functions, where we explored the basics of Boolean logic and learned about George Boole's contributions to mathematics and computing. We covered the fundamental logic functions including AND, OR, NOT, NAND, NOR, XOR, and XNOR, which are essential for understanding PLC programming. Your engagement and enthusiasm for the material were evident, and I am confident that you will carry this knowledge forward as we dive into the world of PLC programming languages in the next lesson. I invite you to join me for the next lesson, where we will explore the different programming languages used in PLCs, their features, and how they are used to create complex control systems. Thank you again for your attention and participation. I look forward to continuing this journey with you as we delve deeper into the fascinating world of PLCs. Please note that all audio and text materials in this course have been reviewed by Professor Roberto Araujo Lima, the developer of the PLC course. His expertise and experience in the field ensure that you are receiving accurate and up-to-date information on PLC programming. If you have any questions or feedback, please don't hesitate to reach out to Professor Lima directly. He is always happy to assist you in your learning journey and provide additional support as needed. Thank you again for choosing this course as your guide to the world of PLC programming.